Here is another semi-recent result. I'm going to call it Elzer's sums. It's several connected results. So here is a result found by Veit Elzer. I think this is how you pronounce him if he's German. In 1984, as a lemma for his work in statistical mechanics. So this is Elzer's theorem in my restatement version of it, because he states it in a fairly different language, but for me it boils down to the following. Let G be a multigraph, undirected node, with at least one edge. Fix a vertex V. If F is a subset of E, then an F path shall mean a path of G such that all edges of this path belong to F. In other words, it means a path of the spanning subgraph V, F, phi restricted to F. If E is an edge and F is a subset of G, then we say that F infects E if there exists an F path from V to some endpoint of E. Now, so this definition is a little bit counterintuitive. I will give an example shortly. So, of course, the terminology is inspired by the idea that you have some infectious disease, that some infectious disease starts at V and spreads along the F edges. So F infects E if the disease at some point arrives at an endpoint of E. So note that if an HE contains the vertex V, then any subset F of E, even the empty set, infects E, because V is a trivial path from V to V, and it's a trivial F path. So there is a lot of like infections that don't really mean anything because the trivial path works. So the claim is the following. Again, it's a sum of minus ones. You're summing over all subsets F that infect every edge. And the claim is that the sum, again, minus 1 to the size of F is 0. So let's see an example. Let's look at the graph C4, the 4 cycle. So here are the vertices. I'm going to give them names, and the vertex that I will name V, it will be the vertex V. So yes, so V is, of course, this vertex. And let me draw the edges too. And I will also name the edges, because this is all about sets of edges. I will name them clockwise, 1, 2, 3, 4. So what can we say about this? So let's G be the graph on the right. Let V be the vertex labeled V. Then the subsets of E that infect every edge are. So let's look at the subset where I only have the arc 1, the edge 1. So my infection is allowed to spread along the edge 1. In this case, of course, the edge 1 is going to be infected. The edge 4 is also infected because the infection starts at V, and V is already an endpoint of 4. And the edge 2 is infected because it gets from V to P using the edge 1. And so it's at P, which means that the edge 2 is infected. However, the edge 3 is clean neither of its endpoints has an F path to V. So the set that consists entirely of the H1 is not it does not cause a pandemic. It infects only 3 of the 4 edges. So that one is not a good subset. However, you can check that these subsets, each of the subsets that I'm typing in, have the properties that they infect every edge. And what is the sum? Well, now that we know that the sum, what the sets are, you have to take -1 to the 2, because this is a 2-element set, plus again -1 to the 2, plus again -1 to the 2, plus -1 to the 3, 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 plus -1 to the 4, and it turns out to be 0. So, remark, it might appear more natural to study subsets F infecting vertices rather than edges. However, the above theorem would be false if we replaced every edge by every vertex. The graph above actually provides a counterexample. Or not above, the graph on the right. However, if we go further and replace this infectious set by a set of vertices, then we get something true again. See below. So how do we prove Elzer's theorem? Well, Elzer's proof is somewhat complicated. I give a different, which is, I think, nicer proof in a recent paper, which is elementary and nice, if I may say so myself. And this is not a very hard result. You should probably think about it on your own, and there will also be a hint in the notes. Elzer's theorem too can be generalized. One direction in which we can generalize it is the same as with the previous result. We strengthen it to a topological statement about the simplicial complex of the pandemic causing subsets, the subsets that are in the sum. Now you will say, hey, they're not a simplicial complex. Their subsets are not. There's a subset of a pandemic causing subset is not a pandemic causing subset. Well, yes, it's not. So you have to read superset for subsets, but basically it's a simplicial complex turned upside down. So see this paper for details. Another venue is to replace our patient 0, V, by a set of vertices. So instead of the infection starting only at V, you now started at a whole set of vertices, and then you look at which edges get infected. This gives a much less trivial situation. See another recent paper for some work on this, including some open problems. This was, I think, the result of an RU project. Galen, Dorpel, and Berry is one of the authors I know best, and there's others. And finally, yet another direction is to ask yourself if this is really about graphs and edges, or if there is some more fundamental structure behind our graphs, that our graphs are merely a particular case of. So in other words, can we generalize Elser's theorem beyond the setting of graphs? And this is exactly what I did in this arXiv paper. So this is actually the trick, if you want. So basically, this is not really a graph theoretical question. It turns out to be a question about something I call shade maps, which has lots of different instances, and one of them is edges and graphs. I will not explain the generalization here, but let me state one more first. So one more particular case of it, which replaces edges by vertices throughout the theorem. And now you have to be a little bit careful with how you replace it, but otherwise. So let me call it vertex Elser's theorem. So again, we have a multigraph and we fix, and instead of at least one edge, we need at least two vertices. Fix a vertex. Now, instead of looking at paths using a given set of edges, you look at paths using a given set of vertices. If W is a subset of V, then a W vertex path shall mean a path P such that all intermediate vertices of P belong to W. We call it the intermediate vertices of P mean all vertices of P except for the starting and ending points. Note also that any path of length at most 1 is automatically a W vertex path because it has no intermediate vertices. Again, we have to define a notion of infection. So if W is a vertex, and I'm going to exclude V because V is in a way obvious here. So if W is any vertex, and the capital W is any subset, then we say that capital W vertex infects little w if there exists a W vertex path from V to W. So basically, now infection spreads through vertices. It spreads from each vertex to each neighbor. And the question is, is your vertex set enough to connect the source of the infection, so V, with the point W? So notice that this is always true when W is V, when W is a neighbor of V. And the claim is that the sum over all set W that infects, well, vertex infects every vertex W in V without V. This is again 0. And notice that I'm not, so the vertex V itself is not invited into the subset because it wouldn't make a difference in it. It wouldn't appear as an intermediate vertex anyway because it's the starting point of those paths. So if I allow this vertex V in W, then this equality would be obvious and uninteresting because you could just toggle it in or out of the path and you would get, so you would get two copies of each set, one with an even size and one with an odd size. But interestingly, it's true even if I don't allow V. Yes, so much for the Elser's theorems.